So in this lesson, we are going to go ahead and discuss Lagrange's theorem as well as lay the foundations for the primitive root theorem, which will be covered in our next lesson. So the Lagrange's theorem that we will be proving is actually what is generalized and becomes the Lagrange's theorem that is covered in abstract algebra. So you have seen abstract algebra already. The result we're going to cover today is its first formulation. And if you have not taken abstract algebra, highly recommend once you take it to come back to the statement and see how different the two are. But as one thing that we will see as the course goes on is that this theorem is going to continue popping up in our results, and little by little we're going to start to see that thread that eventually generalizes to what is covered in abstract algebra, even though we won't be covering its most general formulation. So the story of Lagrange's theorem actually begins with some of the stuff that we have been discussing, specifically Wilson's theorem. So Lagrange proved Wilson's theorem by applying this statement that he proved. But what he was actually trying to do was not prove Wilson's theorem, but a conjecture which today is known as the fundamental theorem of algebra. And so the statement goes back to Albert Gerard in 1629. And so if we look at a polynomial like x squared plus 1, we know that this has no roots over the real numbers, but if we allow ourselves to go to the complex numbers, then it has roots, because we can factor this as x plus I times x minus I. So Gerard conjectured that if you have a polynomial of degree n, and we are counting multiplicity, then we would have exactly n roots counting multiplicity over the complex numbers. So in this case, we have x squared plus 1, and we have two roots, negative I and I. And that's exactly what Gerard conjectured, that this should be true in general. And its story actually has several famous mathematicians who thought that they have proved this conjecture only to be found in error later. And so Euler gave an incorrect proof in 1749. De Fontenay in 1759 gave also an incorrect proof. Lagrange proved his Lagrange's theorem that we'll be covering today in 1771, and a year later he published a proof of the fundamental theorem of algebra, which was also found to be incorrect. Laplace, who was Napoleon's minister of the Interior, also published a proof that was wrong, and Gauss in 1799. So all of these proofs initially were thought to be correct, and then an error happened. And it's worth noting something that connects back to structures, and that we discussed at the beginning of the term. We have to be careful in judging these mathematicians for their work being incorrect, is that they did not have a rigorous foundation for the subject. And so that came later with the work of Cantor. And so a lot of the arguments that these mathematicians published was based on intuitive arguments and not all the times justified, to the point that Euler got into a row with another famous mathematician of the time, D'Alembert, because D'Alembert accused Euler of using infinite series without even knowing if it made sense. And in the process that led to what we cover in calculus with the comparison test, the ratio test, and checking for convergence. And so that came out of an argument that D'Alembert had with Euler, because the way Euler approached infinite series was without any care as to whether they converged, but just manipulating them and finding formulas for them. And so that those questions that we are drilled in calculus came much later. And so as a consequence, each of these mathematicians was basing it on their own intuition for certain parts of the arguments, and there were claims that were not fully justified and were incorrect. And so finally, in 1813, the first proof of the fundamental theorem of algebra was discovered by John Robert Argand. And this is actually the same person who introduced polar coordinates as we cover it in calculus for computing double integrals and just polar coordinates in general. And so the statement in its general form says that if we have a polynomial, degree n, and so we're writing it in this way, then we can always factor this into the form z minus alpha 1 times z minus alpha 2 all the way to z, and this should be an alpha n, that's a typo, where each of these alpha i's is a complex number, and moreover we have a unique factorization. And so this is the analog of the fundamental theorem of arithmetic. Fundamental theorem of arithmetic, every integer has a unique prime factorization but up to a negative sign because we could have a negative number, but we have a unique prime factorization. Similarly, if we're looking at a polynomial, we have that its factorization into these linear terms is also unique. And so in abstract algebra, one generalizes these notions and views these as the extension of prime numbers over in the set of polynomials. And so we're going to touch slightly on these sort of generalizations at the end of the term when we talk about the Gaussian integers. So let's go ahead and make some terminology. So whenever we say a polynomial, we're going to be proving Lagrange's theorem, but we're going to be doing it in a more general setting. So we're going to go ahead and take K to be a field. So as a reminder, we say that a ring R is a field if each non-zero element of R has a multiplicative inverse. So for instance, we have that the following are fields: the real numbers, the rational numbers, the complex numbers, but we also saw earlier that the integers modulo p with p prime is also a field. And so what we are going to do is an instance of how arguments in abstract algebra go. It turns out that to prove Lagrange's theorem, we can just do this over any field. We can do this over the real numbers, rational, complex, and the integers modulo p, and the proof is exactly the same. The only thing that changes is the set that we're working in. So why not just call the set R abstractly? And so long as we know that R has multiplicative inverse, the proof is going to follow verbatim. And so we're going to allow ourselves to work over a field rather than over a specific set. And so that's just something to be mindful here, that why we're going about this in a more general setting. So we have our polynomial, and we're going to say that the degree of the polynomial is d if the leading term ad is of course non-zero, and we're going to go ahead and write the degree of f of x as degree of f of x. And so we have degree of x squared plus 1 is going to be 2. And so this is just a formalization of what we are used to. But something to note is that 0 has no degree. The 0 polynomial has no degree. Because to get the 0 polynomial, we would need each of the coefficients to just always be 0. But our definition is stipulating that we have a non-zero coefficient. And so 0 polynomial does not have a degree, but a common convention in math is that the 0 polynomial has negative, that the degree is negative infinity. And so that's just a small convention that we are not going to be touching upon, but in a future course, you may run into this definition that the degree of 0 is negative infinity. So let us go ahead and move on. So the first statement we're going to state, but we will not be proving today, is the division theorem for polynomials. So you will be assigned this question as one of your future quizzes. And so what the division theorem for polynomials states is that if you have f of x and g of x, these are polynomials defined over a field k of degree d and m respectively, then we can find polynomials q of x and r of x over the field k such that f of x is equal to g of x, q of x, plus r of x, and then r of x here is the remainder. And so r of x is going to be 0, or the degree of r of x is less than the degree of g of x. Now this result can be proven by induction, and one of the key ideas for it is that in the case when m is less than or equal to d, to use the induction hypothesis, it's useful to make this substitution. Let f1 of x equal f of x minus this quantity here, where what we have done is multiplied by ad times bm inverse to g of x. And in doing so, we go ahead and get rid of the b sub m, and so we go ahead and introduce into the leading coefficient in a sub d, and because m is less than or equal to d, we have that d minus m is non-negative, and so we then get that multiplying x times d minus m to here is going to result in the leading term having degree x to the d. F of x minus this is going to result in the degree d term being cancelled off, and so you're going to have a polynomial of degree strictly less than d, which will in turn allow you to use the induction hypothesis. And so that's the hint for the quiz. And so now with this statement, before we continue, I'm going to make a couple of remarks. This generalization here is again in the theme of some of the results that we're covering, that they are eventually generalized to arbitrary rings. And so there are rings where the division theorem holds axiomatically, and so these are called the Euclidean domains. And so these are the types of things that would extend the integers as well as these rings of as these fields with polynomials over here, the set of polynomials which is itself a ring. And so those are things that you'll cover as part of a course on abstract algebra. And so we're seeing their first instances here. So now we're ready to prove the famed Lagrange's theorem. So the statement says that for K a field, a polynomial of degree d has at most d roots in the field K. So how do we prove this? So we're going to be using the division theorem for polynomials. So we're going to be assuming this. And the way that the proof will go is in two steps. So the first step is that we want a result analogous to what we know for the integers. We know that if n is divisible by k, then we can write n as k times some other integer. And we wanted to say the same thing for a polynomial. Specifically, if we have a polynomial f whose root is alpha, then we have that x minus alpha is going to be a factor of the polynomial. And so we're going to use the division theorem for that. So that will be the first part of our proof. Then the second step will be going about it by induction on the degree of the polynomial. And that will allow us to then use the first statement that x minus alpha is a factor to apply our induction hypothesis. So let's go ahead and get started. So here's the proof. So we're going to go ahead and first let's get the easy case out of the way. So suppose f of x does not have a root in k. But if this is the case, we are done. It has no roots. This satisfies the theorem, so we're done. So then there's nothing to show. So let's go ahead. So suppose that alpha is a root of f of x. So if it's a root, we have that f of alpha is equal to 0. And over here, this alpha is in the field K. So everything we're working over this field. So if we're working over the real numbers, alpha will be a real number. And now what we are going to do is apply the division theorem to x minus alpha. So by the division theorem, so this is specifically the lemma 1.12.2, we have that there exist polynomials q of x, r of x, with r of x being equal to 0, or the degree of r of x being strictly less than the degree of x minus alpha, which is equal to 1, such that we can write f of x as x minus alpha times q of x plus r of x. But now over here we have that either r of x is equal to 0 or the degree of r of x is less than 1, so it has to be 0. So in both cases, we have that r of x is a constant. So in particular, r of x is equal to c for some constant in the field K. And now we're going to go ahead and plug in alpha. So this gives 0, which is f of alpha, since we have that's a root. And then we're going to have alpha minus alpha, which is 0, times q of x, plus r of x, which is the constant c. And so we have that c is equal to 0. And so therefore, f of x is equal to x minus alpha times q of x. So this gives us our first part of what we want. Now we have that x minus alpha is a factor of f of x. Now we're going to approach this by induction. So next we're going to let S of d be the statement if f of x has degree d, then f of x has at most d roots. So we're going to do this by induction. So the base case is true. Is true since a degree 0 polynomial is a constant function. This constant polynomial which has no roots. So let us go ahead and suppose the following. So suppose this is true. S of n is true. And we are not using n. So we are good. So n is not being used in any of my symbols. So suppose S of n is true. For some n. So we have this here. So now what we are going to do is consider a polynomial of degree n plus 1. So now let f of x, the degree of f of x, equal the n plus 1. So this is the degree. And then as before, if f of x has no roots, then S of n plus 1 is true. So instead, suppose f of x has a root. And let's go ahead and call that root alpha again. By the start of the proof, there exists a polynomial q of x such that f of x is equal to x minus alpha times q of x. And so we have this here. But now the degree of x minus alpha is degree 1. So that means that q of x has to be degree, since when we multiply polynomials, the degrees add up. So this has to be degree exactly n, since f of x is degree n plus 1. So then, the degree of q of x has to be exactly n, And therefore, by the induction hypothesis, we have that Q of x has at most n roots. So let me go ahead and has at most n roots, but now every root of Q of x is a root of f of x, and therefore f of x has at most n plus 1 roots, which shows that s of n plus 1 is true, and thus s of n is true by the principle of mathematical induction for every natural number n. Well, specifically for every non-negative integer. And so we are done. We have proven the famed Lagrange's theorem. And now, with this theorem, Lagrange went on to prove Wilson's theorem, and then also proceeded to, the year after, to attempt to prove the fundamental theorem of algebra, which was incorrect. But we will now go ahead and see how Lagrange, at least in the modern write-up, how he used this result to prove Wilson's theorem. So Wilson's theorem, recall, is the statement that we have p minus 1 quantity factorial, that congruence is the same as negative 1 bar in the integers modulo p. So how do we prove this? So the proof goes as follows. So recall that since p is prime, we have that the integers modulo p is a field. Now we're going to look at the following polynomial. So here, let's go ahead and consider, so next, let f of x be the polynomial x to the p minus 1 bar. So be a polynomial defined over the field. By Lagrange's theorem, f of x has at most p minus 1 roots. Now, let a bar be a reduced residue of the integers modulo p. So if a bar is a reduced residue, we know that there's exactly p minus 1 of them. So there are exactly and so this is the Euler phi function of p in the new notation. So there are exactly p minus 1 reduced residues. And by Fermat's little theorem, we have that f of a bar for the reduced residue is a bar to the p minus 1 bar, which is 1 bar minus 1 bar is equal to 0 bar. And so therefore, a bar is a root of the polynomial. But if the polynomial has is at most p minus 1 roots, and we have just found all of them, because we chose an arbitrary reduced residue and showed that it's a root of this polynomial. So x minus a bar divides f of x for each reduced residue a bar. But if we apply the statement that we proved over here in succession, so specifically we have a root, we can go ahead and use the division theorem to get x minus alpha times q of x plus r of x and then show that this here is 0. What we end up getting is a factorization. So as a consequence of that proof, we see that the following, that f of x has the following factorization, where we just go ahead and have all the reduced residues, which are all the elements going from 1 to p minus 1. So x minus 1 bar, x minus 2 bar, all the way to x minus p minus 1 bar. And so we have that this is the factorization for f of x. Now, let's go ahead and plug in 0. So we plug in 0 bar there. We're going to have negative 1 times a negative 2 bar all the way to p minus 1 negative of this. But now we have p minus 1 copies of a negative happening over here. So we can go ahead and factor this out as a negative 1 bar to the p minus 1 times p minus 1 factorial that congruence class. So we have this here. By Fermat's little theorem, we know that negative 1 to the p minus 1 is going to be just 1. So we have that this is p minus 1 factorial. And so if we evaluate at 0 bar, we get back p minus 1 quantity factorial. But we also know that x to the f of x is x to the p minus 1 minus 1 bar. So if we go ahead and plug in 0, we end up getting that this side over here is negative 1 by definition of f of x. So now we end up getting that p minus 1 factorial is equal to negative 1, which finishes the proof of Wilson's theorem in the manner that Lagrange proved it. And so this is how we are going to be applying Lagrange's theorem. Here we were able to look at a polynomial, specifically x to the p minus 1, and Fermat's little theorem allowed us to find all the roots and consequently factor the polynomial. And so that's going to be a recurring theme when working modulo p, is that we can find, if we want to factor a polynomial, and we know that we can go all the way up to its degree in terms of its roots, we can go ahead and just write it off in terms of its linear factors. So now, we're going to move on and consider the following. So we just saw the case of x to the p minus 1. But we could also do this where we take x to the m, for m some other natural number, and consider what happens if we take x to the m minus 1 bar. So we did p minus 1, we have exactly p minus 1 roots. But in general, from Lagrange's theorem will tell us that this has at most m roots. So, in the following result, we're going to go ahead and generalize this to be able to deduce what are those m roots in the integers modulo p. So now we want to go ahead and consider the integers modulo 13. And we want to ask, how many congruence classes are there whose fourth power gives us back 1 bar? We can do this by hand, of course, but say that we only wanted to know how many numbers are there. We don't care what those are necessarily. One way of going about that is by factoring out the polynomial. So let's bring the 1 bar over to the other side. And so we're looking at the equation x to the 4 minus 1 bar. But this is a difference of squares, so we can go ahead and factor this as x squared plus 1 bar, and then x squared minus 1 bar. But we can go ahead and factor that even further. And so we have this here. So we know that -1 and 1 satisfy this, so that gives us two numbers, and Lagrange's theorem tells us that there are at most two more from the x squared plus 1. Well, can we establish that those exist? A way of doing this is by doing the following. So the proof of Wilson's theorem tells us that every single element of the integers modulo 13 is going to be, well, sorry, not every element, but every non-zero element is going to satisfy the equation x to the 12 is equal to 1 bar. So we know that this has exactly 12, we know that x to the 12 minus 1 bar equals to 0 will have exactly 12 roots. So we know this by Lagrange's theorem coupled with Fermat's little theorem, as we just saw in the proof of Wilson. It turns out that this has 4 roots, so we found already 2 of them, 1 and -1, so we see 1 and 12. But we also can find by trial and error that 5 and 8 will satisfy are going to be roots for x squared plus 1 bar is equal to 0 bar. But we could do this another way, which is making an observation of an identity. So specifically, we look at x to the 12 minus 1 bar, and we divide that by x to the 4 minus 1 bar. Long division results in the following polynomial. And so we now have x to the 4 minus 1 bar at the front, and we have this polynomial over here, which is of degree 8. Now let's think about this through Lagrange's theorem. We know by Fermat's little theorem, this here has exactly 12 roots. But now this here has at most 4, and this here has at most 8. But because we have exactly 12 roots, that means that this has to have exactly 4 roots, and this has to have exactly 8 roots. And so we deduce from this that x squared plus 1 bar actually does have 2 roots here. And so we now can conclude that this has exactly 4 roots, without having to do trial and error. And so this is very useful when we are considering the integers modulo p or modulo n for a large number n that we don't want to do by trial and error. But instead we can deduce the existence of how many fourth powers or squares are there. And so that's where we are going to be headed. And these are the questions we're going to be focusing on. So now let's go ahead and abstract what we just saw with the previous example. So specifically, we're going to show this result of Gauss, which is really the predecessor to what is oftentimes referred as Lagrange's theorem in abstract algebra. So what this statement says is if we have a prime number p, and m is a natural number, then the equation x to the m is equal to 1 bar in the integers modulo p. This equation has exactly m solutions if m divides p minus 1, and for any natural number m, then we have that the exact number of solutions to the equation is given by the GCD of m and p minus 1. So how do we prove this? So the proof is going to follow a very similar trend to what we saw in the last example. So in the last example, we had this here, and what we did was look at x to the 4 minus 1. And the way we went about this was by looking at this very nice factorization of x to the 12 minus 1. So we used x to the 12 minus 1 because we know from Fermat's little theorem that there are exactly 12 roots there. And in the case of 4, then we have that there are, by Lagrange's theorem, there's at most 4, and then the second polynomial here must have at most 8. And so together we must have that that is equal to p minus 1. So let's go ahead and do the same argument for this proposition. So Let's go ahead and suppose that m divides p minus 1. So we're going to do 1 first. So by assumption, m divides p minus 1. So there exists some k in the naturals such that p minus 1 is equal to mk. Now we're going to consider x to the p minus 1 minus 1 bar. And if we do polynomial long division, we can establish that this here is going to be equal to x to the m minus 1 bar times, and now we're essentially here we're just doing what we did on this step. So what we're going to have is that now this is going to be x to the k minus 1 times m and then we're going to count down. This is going to go x to the k minus 2 times m all the way, and then we're going to eventually get to like x squared, x2m plus xm, and finally 1 bar. So let's go ahead for, just to reference this polynomial in a better way, let's go ahead and call this g of x. We know by Fermat's little theorem and Lagrange's theorem that x to the p minus 1 minus 1 bar has exactly p minus 1 roots. Therefore, the product of x to the m minus 1 and the product of g of x, that has p minus 1 roots. Therefore, the right-hand side has exactly p minus 1 roots. By Lagrange's theorem, x to the m minus 1 bar has at most m roots, and x, and then g of x has at most k minus 1 times m roots. By construction, so we also have that m plus k minus 1 times m is equal to m times k, which is equal to p minus 1. So that's why we define p minus 1 to be m times k. So the only way that we are going to have that there are exactly p minus 1 roots, which is what we have by Fermat's little theorem and Lagrange's theorem, is if this one here has exactly m, and this one here has exactly k minus 1 times m. And so, x to the m minus 1 bar has exactly m solutions, which is what we wanted to show. And then we also have that g of x has exactly k minus 1 times m solutions. And so we are done with this. Oops, that was supposed to be a k minus 1 times m. So let us continue. Let's now look at the second statement. So we now want to show that x to the m is equal to 1 bar has exactly GCD of m comma p minus 1 solutions. So the way we're going to approach this is by making the following claim. a bar, so we want to prove that a bar to the m is equal to 1 bar if and only if a bar to the d is equal to 1 bar, where d is equal to the GCD of m with p minus 1. So we have this here. So how do we do this? Well, we see that this implies that a bar is a multiplicative residue. So, but before we do that, I'm going to just go ahead and use Bezo's lemma. By Bezo's lemma, we're going to use that to get an equation. So we can find integers x and y such that p minus 1 times x plus my is equal to d, since that's the GCD. So we have this here. Now we're going to go ahead and do this in the following way. So suppose that we have a bar to the m is equal to 1 bar. Then a bar to the d, by Bezo's lemma, this is going to be a bar to the p minus 1 times x times exponent rule, so it's going to be a bar to the m times y, which I'm going to go ahead and bring this y over, and this x, I'm going to bring it up above, so we have this here. We have this. But a bar is a multiplicative, is a reduced residue because it has a multiplicative inverse. From this equation, we can go ahead, factor an a bar to out, and we have a bar times a bar to the n minus 1. So a bar has a multiplicative inverse, and therefore a bar to the p minus 1, since a bar has to be non-zero, is equal to 1 bar by Fermat's little theorem. And now we have that this here is 1 bar for the first one, but we also have a bar to the m, but that's our assumption, so that's 1 bar. So we have 1 bar to the x, and then 1 bar to the y, but that's just 1 bar. So in other words, a to the d is equal to 1 bar, which concludes the first part of the claim here. So next, so conversely, suppose a bar to the d is equal to 1 bar. Well, this one's easier because we know that d divides m. So we have here, since d divides m, there exists some integer L such that m is equal to d times L. But then we have that a to the d, or specifically a to the m, is equal to a bar to the d to the L, which is equal to a bar to the d to the L, but a bar to the d is 1 by assumption, so this is 1 bar to the L, which is 1 bar. And so that shows the claim. And so what we have to do now is use part 1 to finish off the proposition. So I'm going to go ahead and make this restricted. Okay, so now by part 1, x to the d equals 1 bar has exactly these solutions, and by the claim we now conclude that x to the m minus 1 bar has exactly these solutions. And so now we are done with the proof, Because this has exactly these solutions by part 1, we know that if a bar to the d is equal to 1 bar, if and only if a bar to the m is equal to 1 bar, so all the solutions that have a bar to the m is equal to 1 bar satisfy this equation. And there's exactly d of those, so we have that x to the m minus 1 bar has exactly these solutions. And so now we have completed the proof of Gauss's proposition. And this is the, as I mentioned, the first instance, at least in the modern reformulation of Lagrange's theorem. And so we're going to come back to this result as we continue working through our results in modular arithmetic and leading towards quadratic reciprocity, which will be the focus for the next couple of weeks. So in the next lesson, we're going to be proving what is called as the primitive root theorem. So I'm going to go ahead and finish today's lesson by making some comments on terminology that we will establish in the next lesson. So specifically, what it means to be the order of an element in the integers modulo n. And so given some n, so some natural number n, and a congruence class that is a reduced residue of the integers modulo n, we say that the order of a bar is the smallest positive integer such that a bar to the r is equal to 1 bar. And we're going to be denoting the order of a congruence class by this notation, or order of a bar. And so that's just the smallest exponent to which we can raise a bar to get back 1 bar. So in the case of Euler's theorem, we know that a to the phi of n is congruent to 1 mod n. And so that gives us an upper bound for what the order can be, but it can be smaller. And so that's where we are going to be proving, is like, what are the conditions on the order? And that's our first statement over here, the proposition 10.1.3, which tells us that if we have two natural numbers n and s, a bar is a congruence class of the integers modulo n that is a reduced residue, then we have that a bar to the s is equal to 1 bar if and only if the order of a bar divides s. So how do we prove this? So let's go ahead and prove the proposition, then we'll come back to the corollary right below it. So just to make things simple, let's go ahead and let m be the order of a bar. And so we have this here. So we're going to go out and do the forward direction. So assume that a to the s is equal to 1 bar. What we are going to do now is apply the division theorem to both s and m. So by the division theorem, we can find integers q and r in z such that r is going to be 0 less than or equal to r less than, in this case, m. And we have the inequality that s is equal to m times q plus r. So we have this here. So now we have that 1 bar, which is equal to a bar to the s, is the same as a bar to the m times q times a bar to the r. So we have this. But we can go ahead and factor out, well, not factor, but we can take out the q bar, the q from the exponent over here. So we're going to go ahead and use exponent rules. So we have that this here is the same as saying a bar to the m to the q times a bar to the r. But m is assumed to be the order. So m is the order, so that means that this has to be 1. 1 bar to the q, a bar to the r. So we got this here. And so this is equal to a bar to the r. And so we got this. So now a bar to the r is equal to 1 bar. So where do we go from here? We have a bar to the r is equal to 1 bar. But the definition of the order is the least value that we can raise it to get back 1 bar, the least positive integer. But r is less than m. Since r is less than m, we must have that r is equal to 0, because otherwise we will be contradicting the order of a bar. And so thus, s is equal to m times q, which shows one direction. The converse is quite easy. So for the converse, we now suppose that m, which is the order, divides s. Then we can find some integer k such that s is equal to m times k. We have this here. Then taking a bar to the s is the same as taking a bar to the mk, which is the same as taking a bar to the m to the k, which is 1 bar to the k, which is 1 bar. And so that shows that a bar to the s is equal to 1 bar. And so we are done with our proof. And so let's now focus on the corollary. So the corollary to this is the following. If we now take n to be a natural number, a bar a reduced residue, then the order of a bar divides phi of n. Well, now this follows because we now have, by Euler's theorem, a bar to the phi of n is equal to 1 bar whenever a bar is a reduced residue, which is our assumption on A. And then by the proposition that we just proved, we now have that the order, so in other words m, well, the order of a bar has to divide phi of n. And so we are done. Because now in this case, s is taking the row of phi of n, and so the order of a bar divides phi of n, and that's what we wanted to prove, and so we are done with the statement. For homework, you're going to be tasked with proving the following lemma, which states that given a natural number n and a congruence class in the integers modulo n, then if s is the order of a bar, then we have that for every natural number j, we have that the order of a bar to the j is s over the GCD of j comma s. And so this here will be proven as part of the homework in chapter 10, specifically 1.13. And so in the next lesson, we're going to go ahead and discuss primitive roots in more detail and build to be able to prove what is known as the primitive root theorem. And so a primitive root, and we'll go over this in more detail in our next lesson. So this is, we have a prime number p, and then we're going to be choosing congruence classes in the integer modulo p that are non-zero. So those elements from 1, 2, 3, all the way to p minus 1. And we will be saying that an element in a congruence class a bar is a primitive root if the order is equal to p minus 1. And so we'll be calling those numbers primitive roots modulo p. And so that's the goal for our next lesson, is to study this in further detail.